Welcome to Lecture 7. When we engineer networks, we start with a baseline truth. Public networks, like the Internet, are open by design and therefore inherently insecure. Data in transit faces three immediate threats. It can be intercepted by an eavesdropper, its contents can be distorted through unauthorized modification, and the source itself can be spoofed by an impersonator. We counter these threats through cryptography. This is the application of mathematical mechanisms engineered to protect data and verify identities within hostile environments. Without these mathematical interventions, digital actions, from sending an email to executing an online banking transaction, remain entirely exposed. In a raw network, trust is impossible. Network security operates as a matrix of four distinct cryptographic services that must be fulfilled simultaneously. The first quadrant is confidentiality, ensuring data remains accessible only to authorized users. The second is integrity, detecting if data is altered during transmission. The third, authentication, verifies the source's identity. Finally, non-repudiation creates an undeniable record, preventing senders from denying actions. This lecture maps specific mathematical primitives, hashes and ciphers, to each of these four service requirements. A system that lacks any one of these pillars is mathematically compromised. True security requires the orchestration of all four. We achieve the integrity pillar through a specific cryptographic primitive, the hash function. A hash function like SHA-256 processes any file size, condensing it into a fixed 64-character hexadecimal string. This triggers the avalanche effect. Changing even one bit in the original file scrambled the entire hash into a new sequence, signaling it is no longer authentic. Engineers use this to verify software downloads. By comparing the hash of the downloaded file to the value provided by the source, you can confirm the data arrived without modification. Note that hashing proves a file is unaltered, but it does nothing to hide the contents. Integrity ensures the message is correct. It does not ensure it is secret. To achieve confidentiality, we turn to encryption, which transforms readable plaintext into unreadable ciphertext. In a symmetric architecture, the exact same shared secret key is used to both lock and unlock the data. Algorithms like AES and DES are prized for their computational speed. Their efficiency makes them the standard for protecting massive volumes of data in real time. However, this creates the key distribution problem. Both parties must somehow share the secret key over the same insecure network they are trying to protect. Symmetric encryption is a highly effective lock, but it remains useless if the key is intercepted before it reaches the recipient. To solve the distribution problem, cryptographers developed a system that decouples the encryption process from decryption, asymmetric encryption. This architecture uses a mathematically linked pair. The public key is shared openly with the world, while the private key is kept strictly hidden. The governing rule is that data locked by the public key can only be unlocked by its specific private key counterpart. Reversing this, encrypting data with a private key, creates a digital signature. This proves to anyone with the corresponding public key that the data definitively originated from the owner. These digital signatures satisfy the final requirements of our matrix, verifying identity through authentication and preventing denial of action through non-repudiation. While asymmetric encryption provides the foundation for trust, its mathematical complexity makes it too slow for encrypting large files. Modern secure networks combine both of these systems, orchestrating symmetric and asymmetric primitives into a single, unified hybrid protocol. During an HTTPS connection, the server provides a digital certificate, using asymmetric cryptography to authenticate its identity. Your browser then uses the server's public key to securely deliver a fast symmetric session key. The symmetric system then takes over, encrypting all actual data transfer. This critical handoff, moving smoothly from rigorous identity verification to high-speed data transfer, is the exact sequence that secures the global internet. Cryptography provides the mathematical framework that allows modern networks to function. Hashing provides the mechanism for integrity, while symmetric encryption provides the efficiency required for confidentiality. Asymmetric cryptography builds the layer of trust, enabling secure key exchange, authentication, and non-repudiation. As this matrix shows, every security service relies on a specific mathematical primitive. However, the integrity of this entire system depends on strict key management, An exposed key renders the strongest algorithm useless. Mastering these principles allows computer scientists to move beyond observing networks and begin engineering environments where trust is mathematically guaranteed.